Next up, we've got Julia Gog, who's going to be speaking about vaccine escape and exploring the simplest model. So I'll hand over to you, Julia.
Can you give me a thumbs up if that's visible? Great, thank you. Okay, so I've worked on lots of different bits and pieces over this pandemic, but I thought this would be the interesting one to bring to this meeting on vaccine escape, because it's somewhat forward-looking, and it's also one that I don't think we've worked enough on. I'm going to present a ridiculously simple model, but even that simple model yields some interesting results. But I'm presenting it in the hope that the wider community might run with this. There might be someone on this call who can do something with this. So I'm going to just present 12 slides, but the last slide is suggestions of how to take this forward. This has been discussed among some of us within JUNW, and thus far chiefly Robin Thompson, Ed Hill and Leon Dannon, but there's been others as well. Okay, if I can go to the next slide, there we are. So let's set the scene first. So this is where we are. This is very UK centric to start with. We're in a hot rollout of vaccine. It's an ongoing pandemic, running out vaccine now, but we've got limited rate of supply of vaccine and limited supply of vaccine in the end. So here's hospitalizations per day going through the autumn. It was looking good there, but then new variant. And since early December, vaccines have been rolling out. And this wasn't really a foreseen situation that would be rolling out with a live big peak at the same time. The UK policy was based on what was known at the time. So before this, there was really good evidence the vaccines were disease blocking, stop severe disease. There was very little evidence about transmission blocking. If you remember, the statements at the time were one would expect it to block transmission to some extent, but we don't know. And really no one counted on a more transmissible new variant. So that's where we were. But knowing what we know now, or thinking about the situation in other countries, or what we will know at times of vaccine rollouts, or even maybe in a future pandemic, what should the vaccine priority order be? And let's just think about this unrestricted, what we could have done, what we could do. Is it that we should vaccinate the most vulnerable people, the highest chance of severe disease or death or hospitalization, however you want to measure that? Should we be vaccinating those who are most at risk by being put in the front line at work? Should we vaccinate those who are most needed at work, so if they were off sick it would be disastrous? Or should we vaccinate those most connected with other people? There's some of the options that have been in discussion in wider society. There's really, really complex ethical issues for society in here. And I'm not ignoring them, but I'm saying mathematical modelling can at least tell you the consequences of what you've chosen, what will be the effects. So it's not that we ignore this and we just optimise something. It's we think about the different things that one could be optimising and put the options out there. So let's start to turn this into specific questions. Given a limited vaccine, limited amount of vaccine, who should you vaccinate? Or more generally, given limited rates of vaccines, say you've got X million this week, what order should you vaccinate people in? I'm not going to talk about time between doses, though there was an absolutely fascinating, hard practical question that UK had to answer last month with this. Bringing in vaccine escape into this question is really interesting, and Robin Thompson's been looking at that. I'm not going to answer this, but there's an interesting further question there on at what point is it in a country's even just selfish self-interest to give the vaccine to other countries? That point must come eventually, right? There's no point vaccinating some groups which are really low risk and not going to transmit, as opposed to vaccinating another country to reduce chances of importation or vaccine escape in future. But there's a plot twist on that one, which I will come back to if I remember. So those are the questions. And what are you trying to do with this? So possible objectives. I think the first three are obvious. The fourth one is the one we want to put on the table now. You might want to minimise severe disease or death. So that's the direct effects of mortality, morbidity from COVID. You might care about minimising cases. That means you're considering the wider disease harms, such as long COVID, but also such as things like people being off work or unable to go to school, or anything that if you're a case, it wipes you out from. Of course, this is super topical, thinking about controlling R, with vaccination means that the effective R comes down, which reduces your needs for MPIs. So as we've seen with announcements yesterday, we can be looking at schools reopening in a few weeks' time. And we want to throw in this one: manage the risk of vaccine escape. Your strategies on how you choose to roll out vaccination can mitigate some of these risks of vaccine escape. And a slightly naughty screenshot from yesterday from our esteemed leader, Boris Johnson. There will be some who say it is arrogant to impose any kind of plan on a virus. I don't think it's arrogant. I think you have to try and do what you can. But if you only think about these first 3 points and you don't think about the 4th point, do you know what? The virus is going to do its own thing. You're setting things up for trouble. You know, it's not arrogant to make a plan, but it's bonkers to keep buying your worst enemy lottery tickets and then be surprised when they win the lottery. So controlling vaccine escape. Okay. Let's start to pull this together into a model. This is super, super oversimplified, but just to make sure we're thinking about the same kind of language for the effects of vaccination. This is without vaccination. So thinking about this person here, they can be infected by the population. So this person is susceptible to infection. This person can transmit infection to others, and chance of severe disease. Not dead, but resting. So this could be, you can either think about it as deaths, you can think about it as risk of hospitalization or risk of given hospitalization ICU. There's subtleties here, but let's just think about this as one thing for a minute, some sort of severe outcome. Vaccination potentially modifies all 3 of these points. So I'm going to multiply by theta subscript, sus for susceptibility, trans for transmission, and dis for disease. And you can think of vaccine as having 3 effects here. So reducing susceptibility, so just stopping the virus infecting the person at all, or to the point that you never test positive or there's no real infection taking hold. Stopping transmitting to others, and we can talk about how that can be, perhaps through lower viral load, and or shorter infection. And of course, this is the one we're thinking about, reducing chance of severe disease. So susceptibility reduction, transmissibility reduction, disease reduction. And they're all really more complicated than one parameter, but I'm just thinking of them as one thing here, each of them. When we talk about disease blocking, we're talking about reduced rates of getting infected and becoming severely ill. So some of the wonderful news about studies yesterday, in some sense, is measuring theta sus times theta dis. So it's not measuring whether they became PCR positive, it's whether there was, compared to unvaccinated people, what was the chance of ending up hospitalized with COVID. When we think about transmission blocking, it's the combination of these 2, getting infected and infecting others. So and then the mathematicians on this call will be thinking, okay, you could just merge theta sus into each of these and reduce it to 2 parameters. And I would argue for this purpose, you don't do that because firstly, there's a separate thing of whether someone tests positive. So you want to match this up to cases, but crucially for vaccine escape, you want to think about who has got infected, full stop, because infections in those vaccinated people. So say it doesn't block infection in, but does out, that's different to blocks infection in as well. Okay, so that's some of the language. I'm going to skip through the methods somewhat, but they are really, really short. And if you could kindly imagine that these are beautifully made slides and not my handwriting, that would be fabulous, thank you. So the population model, ridiculously simple. We need some heterogeneity. So I'm doing it the simplest way, splitting just into 2 halves, equal size. Half of the population are, I'm going to call them vulnerable. They have a probability which is V times higher of some severe bad outcome, which could be deaths or hospitalization. I'm just going to call that disease for now. The other half of the population is more mixy, so there's more interactions with both each other and the vulnerable group. So the mixing matrix I'm going to do for strategic reasons like this, so 1 m squared, so between groups is m, within the mixes it's m squared, and m is some number greater than 1. Then you've got to set up some situation. So you can consider R before vaccination. So I'm going to do 1.2 here because that was not unreasonable for when we started thinking about this in the beginning of early January. Now, instantly vaccination, some proportion of each group. So I'm not even doing a slow rollout. I'm doing a sort of delta of rollout, if you like. Consider then total cases, total severe cases, which I'm going to call disease below, and then total cases among vaccinated. Now, this is the key thing for vaccine escape risk, I think. This is a simplification, but I'm just going to focus on this as a measure of putting the pressure on vaccine escape. You've got to consider some time interval for this. You know, you don't sort of integrate this out to time equals infinity. And here I'm going to do 20 mean generation time. So 20 generation time is time from start of one infection to the next person getting infected. So 4 or 5 days for COVID-19. Simulation dodging. Okay, so we've been under, well, I've been under ridiculous time pressure, and I'd like to have sat it down and done this in a beautiful way. But the time pressure, well, it leads to some inventiveness. If I can write down something and I can literally plug it in that hour and get a result out, I'll do it. Here's a way to do that for this problem. So no vaccination, I made this next generation matrix, which is an outer product of 1M, 1M. Now I vaccinate proportion V1 of the vulnerable half and V2 of the mixy half. And now I've got 4 groups, the vaccinated and the vaccinated and the unvaccinated of the vulnerables and the mixies. The next generation matrix you can work out is now still an outer product. You need to take into your proportion V1s. Mixiness is still in there. This vector is sort of susceptibility. So theta sus is in there, and this is sort of input, if you like. So this is transmissibility from those infected. So theta trans appears there. And I definitely like the next generation matrix being an outer product of this kind, because it means immediately it's got rank 1, which means all but one eigenvalue is 0. There's only one which has non-zero eigenvalue, and that would be this eigenvector here. And the eigenvalue is simply the dot product of these two. So superb, you can literally write it down. Hopefully you can see that's going to be true if you make more age classes as well, so long as you start with certain structure of mixing matrix. Dodge even further, don't even run that over time, just write down the integration. Assume crucially here the time horizon is either short, so we're not doing too many generations, or the effective R is less than 1, so we can neglect susceptible depletion. Then we're in straight exponentials. You can translate R to a growth rate, so you can see a plus explainer for how to do that. And in this case, I've just used log R over generation time for my growth rate. And then you can work out the number of cases over the next G generations. It's a simple function of R. You can then use your eigenvector to turn it into cases among the different groups and then determine how much disease there would be and how much infection there'd be among vaccinated people. And I'm going to point out, this is a bit of a spoiler because it kind of tells you what the results are going to be. The time period you're thinking over really matters. So if you're thinking about a longer time period, then any effects from the vaccination that reshapes the epidemic's trajectory becomes really important. So bringing cases down will dominate over any other effect. If you're thinking over a super short time window, you can get a different result. So this is actually an important thing, what time period you're thinking over. And typical outputs. So delightfully enough, this is a 2-minute job in Mathematica to produce. You might think about the total R. So all of these plots like this with these blue and yellow is, you probably can't see, the x-axis is proportion of the vulnerable vaccinated going from 0 to 1, proportion of mixers vaccinated from 0 to 1. So 0, 0, no one's vaccinated, 1, 1, everyone's vaccinated. Any sort of diagonal, anything along this diagonal is half the population vaccinated in some mix. R starts at 1.2, and with these particular assumptions about transmission blocking, it drops down below 1 eventually. Cases, that's a straight function of R, so it's not surprising it sort of looks similar. Diseases and deaths, actually this is not quite the same as this because you've got a higher proportion of bad outcome in the vulnerable. And then this one, right, which I assumed it was a bug when I first plotted it, but no, I'll talk through that and explain why the vaccine escape pressure, i.e. number of infections in vaccinees, is interesting in this way. Just over a few minutes, I'm going to talk about this plot, total disease, and how you might minimise that, and then vaccine escape pressure and what changes that. So say you've got a little bit of vaccine and you're here, so you can go in either direction or some combination of which. And you might think about, okay, my next bunch of vaccination, am I going to do the mixers or the vulnerables? Ratio of disease averted. And actually, it doesn't matter what you take epsilon to be, because this is a pure linear function for this model. And it depends on what you've assumed about relative vulnerability, this V, and relative mixiness, this M. But for this plot, it's plotting M versus V, most of the plot is blue. It's generally better to vaccinate the mixers, right? Ratio of disease averted for these particular parameters. I'm going to show you some more of these plots. So remember, blue is it's better to vaccinate the mixers, red, better to vaccinate the vulnerable. Here, it's a bit complex, but there's a grid of different theta sus, so how much susceptibility stopping it is. So 1 is it doesn't. And transmission blocking. So if you're infected, do you infect others? So 1 is it doesn't, then you go down there. And I hope you can see that basically, apart from this one in the top left, most of these plots are mostly blue. So the bottom line from this simple model is that it's mostly best to vaccinate mixers first when you've got disease transmitting, except when either no transmission blocking is happening by either means, i.e. you're up here, right? If the vaccine doesn't actually reduce cases, then you've got to focus on protecting the vulnerable. Or if M is not much greater than 1, in other words, you're on the x-axis on any of these plots because the mixers really aren't that mixy. So in essence, if vaccination can bring cases down, because you're dealing with a live high prevalence, then this is the priority over the medium term to even protect the vulnerable. If your priority is to protect the most vulnerable, you just want to bring cases down. And the big caveat here is the short-term optimum would be definitely vaccinate the vulnerable first. If you bring that G down, the number of generations down, these would be all red, right? And in some, you might argue that that was UK's situation in late December, early January, right? So we've got other means of bringing cases down, such as imposing lockdowns, in which case your vaccine is there to protect the vulnerable over that short period, whilst you get cases down by another means. This is the interesting one for me. I think the vaccine escape pressure. So proportion of vulnerable people vaccinated, proportion of mixers vaccinated, it's non-monotonic. In particular, if we focus on this y-axis, as you vaccinate more and more mixers, not vaccinating the vulnerables for a minute, sort of vaccine escape pressure goes up and then comes down. But this is actually a classic and old result. So if we go back to Grenfell et al.'s phylogenamics paper in 2004, this is the famous figure 2a. And yeah, I can plot a parabola all by myself. I'm delighted by this. This is within hosts, so it's not quite the same thing. But this is saying that there's more immune pressure, your viral population goes down, but your strength of selection goes up. So you get this sort of unimodal relationship where the middle is the most dangerous for escape pressure or viral adaptation rates. This is the same thing going on at population level. So as you vaccinate more people, there's more people who are vaccinated who get infected, but eventually you bring cases down and that dominates in the end. So I think that's of interest. Intermediate vaccination is a bit risky for vaccination escape. Again, you can look at that over different parameters. This is where there's no transmission blocking, but for all the ones where there's any transmission blocking, it's sort of the same qualitative picture, as long as there's anything going on there, stopping transmission. You can slightly see the same effect going on in the vaccinating the vulnerable, this non-monotonicity, but it's much less marked. But here's the interesting plot twist. Suppose seeing what is the absolute worst strategy, how do you make it so there's the most vaccinated people getting infected? Well, the answer is, in all of these, you go down to this bottom right corner. you vaccinate all of the vulnerable and none of the mixers. That's absolutely your best strategy to put pressure on virus to produce a vaccine escape variant. And that's where we're at in the UK at the moment. We're getting towards the end of vaccinating our most vulnerable groups and starting to think about vaccinating the rest of the population. It's a risky, risky time. So that's a plot twist from other countries. Perhaps we'll be doing something awful if we don't finish the job of vaccinating and getting our cases down. Or if we stop vaccinating after the vulnerable, we've got to get prevalence down. Otherwise, we're producing a real risk of producing an escape variant, which is horrific for the world. So rule of thumb for there, in some sense, you didn't need the model to see that. You can guess at that. So this is the end of where I get to. The simplest, ridiculously simple, no actual time simulation going on, just eigenvectors and integration. Gives you broad brush principles and insights. Specifically, one, vaccine aimed at bringing the prevalence down could be more effective than protecting the vulnerable directly. Two, intermediate levels of vaccination could be the highest risk for pressure to generate a vaccine escape variant. And specifically within that, three, vaccinating the vulnerable groups and not the mixers is the most risky thing you can do for creating a vaccine escape variant. The horizontal line sort of marks the end of what I'm doing or what I've done on so far on this. And it is too simple, and you should criticize me for this, but even better if you do something about it. For this to be considered sound for any application to policy, it's important to explore more realistic assumptions, at least in some key aspects. And I think particularly population structure, half mixers, half vulnerable, that's a really bad approximation for, let's say, the younger people are mixy and the older people are vulnerable. Actually, we understand that structure to some extent. So you will need population details, mixing structure. Here's a nice age structured mixing matrix from the BBC Pandemic Project, which is available to anyone. Understanding hospitalizations, case fatality ratio by age or particular population group. And particularly with the children, understanding susceptibility and infectivity by age is not the same as adults. You'll need an understanding of what the possible intervention strategies are. This is going to be in the context of constant low prevalence, where MPIs are adjusted, or is it going to be constantly R just less than 1? Or are the MPIs, non-pharmaceutical interventions, just going to be kept fixed and the vaccine controls prevalence? Vaccine effect assumptions, here are the simplistic ones I threw in. These need to be elaborated a little bit. And whatever you do, I think sensitivity to this needs to be explored. I think we'll get a clearer picture, but there's still going to be uncertainties, particularly on transmission blocking. And vaccine escape assumptions. And I think that's the hardest thing, both in terms of formulating it and ever parameterizing it. So this will be the hard one, I think, going forward. I hope this is of interest to some of this community on the evolution and epidemiology to take this forward. And I hope that was interesting. Thank you. I'll stop there.
Thanks, Julia. Well, I think it was interesting because it's created a lot of questions and I don't think we're going to get to them all, but hopefully Julia can either type answers in the chat or we can come back to them later. But we'll just do one quick one before we head off. So what happens in the cases where theta trans is greater than 1? So if vaccines make more people asymptomatic transmitters instead of isolated. So that's from Jordan Skittrell. Hopefully I said his name right.
Hi, Jordan. Great question. I haven't been thinking about that. That's a bit horrific. I'll have to think about that. So, okay, I understand the question. That could be the case if, say, the vaccination means the symptoms are less obvious. So someone who's vaccinated actually ends up transmitting more than others. It does horrific things for vaccine escape. You can see that already. You can get some really odd effects going to happen there. I might privately make those plots, but they will scare me. Thank you. Good question.
Thank you. So we are a little bit over time. We have got on the timetable now to have a quick break because I appreciate it's quite a long morning of meetings for you all. So if everyone can, if everybody can come back in promptly at 11:10, and then we will kick off with Leon Dannon. Thank you very much, everybody.